Okay, folks, I want to do a problem from section 6-4. This is the section that talks about how do we use the normal distribution to approximate the binomial distribution. Okay, now obviously I can't do the entire lecture again. I already discussed it previously, but I thought doing an actual problem from the exercises might be of some value. So here's the problem. It's in the section 6-4, the exercises. It's problem number 17. It's called retirement income. Now, as always, these are metaphors. It doesn't have to be retirement income. The same exact process would be done if you're talking about illnesses or anything else. Anything you can think of would use the same exact technique. So here's this problem. It's talking about retirement income, about the total population of American households. 17.3% receive retirement income. You take a random sample of 120 households, and you want to know what's the probability that more than 20 households, but fewer than 35 households receive a retirement income. So think about it in terms of medical, medical issues. Maybe 17% have high blood pressure, 17% are overweight, 17% have some sort of a diabetic condition. Whatever it is that you're talking about might be a little more interesting than retirement income. I also want to point out that it's very important to see this language here. It's more than 20, fewer than 35. This is what we call strictly more than and strictly fewer than. Strictly means we do not include that number. So when we say more than 20, we're saying it's more than 20, not including 20. It's strictly more than 20. And same remarks apply for the fewer than 35. Okay, so let me take a look at the problem. You see the problem, obviously. Give me 1 second here. Just real quick here, that the concept is that this normal distribution here is getting pretty darn close to the binomial distribution. So we can use the normal distribution to do the approximation. Now, the word approximation, what does that mean? That means that it's approximately correct. It's close enough for government work. It's, this is statistics, right? It's not it's not like physics or something where you get an exact answer. These are all not approximate. These are all probabilities. Therefore, it's certainly appropriate to use an approximation. Okay, the only real challenge here is understanding this correction for continuity. I refer to this table right here in my handwritten solutions. So I want you to, if you have any difficulty with this, you really need to look at this table and look at the textbook. So let me go ahead and pull up my handwritten solution. Okay, so here's my, here's my handwritten solution. We're going to use a normal distribution to approximate the binomial distribution. This is section 6-4. It's review exercises number 17. And for the spring of 2020 class, this is your big hint for problem number 11. Okay, so problem number 11 on the final exam is similar to this. Okay, so here's what we're given. 17.3% of the people receive retirement income. The sample size is n is equal to 120. Find what is the probability that out of the 120 households, we have more than 20, but fewer than 35 who receive the retirement income. So I always start, first of all, I try to do a discussion. As always, the discussion kind of has to be whatever's appropriate for you. I didn't put into all the details here. In the book itself, it does give you a procedure table, gives you the algorithm. First thing you do is you check to see whether the normal approximation can be used. Remember what that is this business of, in order for it to be appropriate to use the normal distribution as an approximation, you have to meet a couple of conditions here, which okay, talks about how if P, that's probability of success, if it's close to 0 or close to 1, it really isn't that great, especially if N is relatively small. So it's not really appropriate to use the normal approximation. Here's the rule of thumb. N times P and N times Q have to be both greater than or equal to 5. So I'll let you do that yourself, but certainly we meet that condition. Okay, so what are we looking for? You know, when we're talking about x is strictly greater than 20 and strictly less than 35, what the heck is x? X is the number of successes, okay? It's the number of successes. It's how many people, or how many households receive retirement income. So that's what a success is. So it's a number. Now, the reason it's a binomial problem, the reason it's a binomial distribution, is because you receive or you do not receive the retirement income. So it's kind of like heads or tails, right or wrong, left or right. It's one or the other. You either receive it or you don't. So that's why we call this a binomial type of a problem, a binomial distribution. Well, can you imagine trying to solve this using that crazy formula, the binomial formula? You'd have to do the probability of x is 21, probability x is 22, 23, 24. You'd have to do all those calculations. All those calculations, it would be just way too hard. So what we do is we say, okay, it's close enough for us to use the normal distribution to approximate it, okay? All right, it's too hard to do the problem using binomial distribution techniques, so we're going to use the technique in section 6-4. So here's a solution. For the binomial distribution, okay, for binomial distributions, is a true fact that the mu, the mean of the population, the mu is equal to n times p. So in this problem that we're dealing with right now, that's 120 times 0.173, so that's 20.76. The variance is NPQ, so that's this, and that's the variance. The standard deviation is the square root of that, so that works out to be 4.14. The Z, that's the so-called, what do we call that? The z-score, oftentimes it's called, that's just x take away mu over sigma. That x is the original data point that you're dealing with. You're going to transform. You're going to take this data point x and you're going to transform that into a z-score. So in this particular situation, mu is 20.76, sigma is 4.14. So we're all ready to go here, okay? Now, you know I like cartoons. Here's my cartoon. Our original cartoon, the cartoon for the original situation is this. 20.76 is the mean, and we want to know what's the probability between 20 and 35. Okay, now this is obviously not to scale because 20.76, that's the mean here. 20 is going to be very, very close to the mean. So it's not to scale. It's a cartoon. It's not for analysis. It's strictly a cartoon. Well, we need to deal with a continuity correction because the problem is, if you just plug in the numbers, you're going to be off by a little bit. Because, for example, we do not want to include 35. We do not want to include 20. It's strictly greater than 20. It's strictly less than 35. We don't want to include 20. We don't want to include 35. So we have to use a continuity correction. And that's the table that I showed you on page 355, which, let me see if I can grab that real quick. Here it is. Okay, so if x is strictly greater than some number alpha, it's going to be, we're not going to include alpha. It's going to be greater than alpha plus 0.5. Okay, if it's strictly less than, it's going to be alpha take away 0.5. Okay, so this kind of summarizes what we're doing there. Okay, so we're going to use that table. Our problem that we're doing right now asks for less than 35, i.e., and i.e. means that is, i.e. strictly less than 35. So we do not want to include 35. So this upper bound that we're going to be looking at, this guy right over here that we're going to be looking at, is going to be 34.5. We're not going to include 35. We're going to be a little bit less than 35. And then for similar reasons, the lower bound is not going to be 20, is going to be 20.5. It's going to be a little bit over this away, okay? All right, so now it's all over but the crying, okay? Here we go. If we wanted to include 20 and 35, the bounds would be, 19.5 and 35.5. We would include 20 and 35. So that's a big hint for how to do problem number 11, because I believe problem number 11, we want to include those numbers that we're dealing with in problem number 11. Okay, so now we can move forward. The difficulty is that the normal distribution is too hard to calculate. See, if we knew how to calculate the normal distribution, it'd be easy to do at this point. It's just too hard. It's that very complicated formula. You need to be able to use calculus. It's just too hard. So what we do is we convert everything to the standard normal distribution because we have the table in the back of the book that's going to help us. So we transform, give me 1 second here. Okay, we transform those two boundary points into the corresponding standard normal values. We don't want just the normal values. We don't want the normal distribution. We want the standard normal distribution. And that's the standard normal distribution is the one that has a mean of 0 and a sigma of 1. And how do you get there? You get there using this formula right here. Z is equal to x take away mu over sigma. Okay, so those are the standard normal values are oftentimes referred to as the Z values or the Z score. So we can use that table in the back of the book using this formula. Okay, so that the 20.5, that's the original X value. I'm going to transform that into a Z value. How do I do it? I use this formula. 20.5, take away the mu, divided by 4.14, boom, I get an answer. The 34.5, I'm going to transform that into a Z-score. What do? I plug it into the formula and I get an answer. Boom, there it is. So now this is my new cartoon. My new cartoon is negative 0.06. That's right here. That's just a tiny, tiny bit to the left of the mean of 0. And then 3.32, that's way the heck over here. So that's pretty far over, right? Okay, so that's my new cartoon. I didn't bother to shade it in. It's too hard to shade it in and make sense. But that's my new cartoon. So this cartoon corresponds in a way to this cartoon all the way up here. This is the original data points, and this is the transformed data points. In other words, the Z-scores, okay? So now we're going to use a table to get the areas to the left of this transformed Z-score and to the left of this guy. Okay, those areas are, you look in the table, corresponding to this one is 0.4761, corresponding to this one is 0.9995, okay, respectively. You know what respectively means, I hope, right? This guy is with respect to this guy is with respect to this guy. So respectively, in other words, they correspond in the same order. Okay, this symbol here means therefore. Therefore, the probability that x is between 20.5 and 34.5, okay, now using the approximation, the normal approximation, okay, you just crank it out. Now you got this area here, take away this area here, that gives me this 0.5234. That is equal to 52.34%. So approximately, the probability is 52.34% that between 20 and 35 households, not inclusive, I'm not including 20 and I'm not including 35. So it's 21, 22, 23, and so forth, all the way up to 34. So the probability is 52.34% that between 20 and 35 households will receive retirement income. So if you don't like retirement income as an example, use something else. Use diabetic, low blood sugar. Use, infected with COVID virus, whatever you want to use that makes more sense to you, that is of more interest to you. Okay, so I hope that helps. This is a big hint for problem number 11 on the final exam.